Internal rate of return. Next, we are going to explore using the internal rate of return, IRR, as a capital budgeting tool for deciding how best to invest and allocate money. Internal rate of return is the discount rate used in capital budgeting that makes net present value of all the cash flows from a particular project equal to zero. The higher the internal rate of return of a project, the more desirable it is to undertake that project. The internal rate of return is derivative of NPV, net present value. Net present value basically tells us whether or not the present value of the cash coming in exceeds the cash going out, what we have to pay to get those cash flows in the future. NPV calculates the net of the present value of the cash flows. With IRR, we come at the issue from a little bit different angle. First, we compute an NPV, and then we're going to ask what discount rate sets the NPV equal to zero. The discount rate that makes the cash outflow equal to the present value of the cash inflows is the IRR, the internal rate of return. Our decision rule with IRR is we're going to invest if that rate is bigger than our hurdle rate. Internal rate of return is basically asking how hard do we need to discount the cash flows in order to drive all the value out of the project. It's a measure of the resiliency of the cash flows. The harder we discount, the more that drives down the NPV. How hard do we have to discount it and still stay bigger than zero? That's what IRR is designed to tell us. This decision rule is very similar to our net present value decision, as we'll see graphically. IRR takes the net present value, which is a numeric value, and restates it as a percentage, which makes it more intuitively appealing. It's difficult for us to grasp the meaning of a number. It has little context. If we say the NPV is $3,537,000, it means little by itself. But if I tell you the internal rate of return on the project is 25%, it's easy to intuitively grasp. It takes the net present value and changes it into a percentage that's easier to quickly grasp and understand. It gives us a more intuitive and appealing take on the NPV of the project. IRR doesn't tell the whole story, though, and it's best to always use it in conjunction with NPV. NPV provides the scale, and IRR provides the intuition. So let's think about IRR in formulaic terms. When we had our net present value formula, the NPV was equal to the initial cost weighed against the future cash flows coming in from the project. So the NPV equals the initial costs plus the cash flow in year 1 divided by 1 plus the interest rate, the cash flow in year 2 divided by 1 plus the interest rate squared, the cash flow in year 3 divided by 1 plus the interest rate to the third power, and on and on. That's the formula for NPV. To calculate IRR, take the exact same formula, and instead of using R, the discount rate, we replace that with IRR and set that equal to zero. Set the whole equation equal to zero. The discount rate that sets this series of numbers equal to zero is the IRR. So now we have an equation that looks like 0 equals the negative of the initial costs, right, plus the cash flow in year 1 divided by 1 plus the IRR, plus the cash flow in year 2 divided by 1 plus the IRR to the second power, plus the cash flow in year 3 divided by 1 plus the IRR to the third power, and on and on. Remember, there is a minus sign in front of the initial costs, right, because those are costs. It's really difficult and incredibly time-consuming to solve this polynomial equation for IRR with a pen and paper. There is no direct calculation. It's an iterative process, meaning you have to make a guess, do the calculation, and continually adjust as you overshoot or undershoot the mark. Here is the formula to get an idea of how cumbersome it is to populate and calculate. And this is a really complicated formula. It's 0 plus the sum of all the cash flows, and then in parentheses 1 minus, and then in parentheses again 1 plus IRR to the minus the negative n, and then divided that by IRR, parentheses off, and then multiplied times parentheses times another set of parentheses, 1 plus IRR, plus the sum of all the NQs, and then parentheses, plus the initial cash flow. So you can imagine that's just a crazy formula, right? As you can imagine, IRR was not a very useful tool before financial calculators, computers, and spreadsheets. So this is really a relatively new tool that we actually can use very easily now. It's easy to do now in a spreadsheet or in a financial calculator because they have IRR functions built in. You just put in the range of the cash flows, you make a guess on the IRR, and the computer will chug through thousands of calculations and provide you with the answer in a split second. I prefer Excel or a spreadsheet program on a computer instead of a financial calculator because you can build out the model and save the results. And this is really important if later your boss or client asks, how the heck did you come up with the number? You can always save your work for later reference. Because I guarantee you, later on, a year later, you'll forget what you did. And believe me, I've learned that the hard way. Let's look at the relationship between NPV and IRR. When you have a project and it has a positive NPV, you can graph that value of the net present value in dollars. And then as you continue to discount the cash flows with progressively higher and higher discount rates, the NPV is going to decline until at some point it crosses over zero. And the point at which it crosses over zero, the discount rate that sets NPV equals to zero, that's the IRR. So anytime the discount rate is below the IRR, it's a positive NPV project, right? Every time the discount rate is below IRR. So if our hurdle rate is 7% and the IRR is 12%, it's judged to be a good project, right? In that case, the IRR is 5% higher than our hurdle rate. IRR is similar to NPV, except that we have discounted the cash flows to a percentage rate where the discounting just crosses to zero. Now we can say, for example, the return on this project, the IRR is 12%. And that's easier to understand than saying the net present value is $1,613,672, which is just a big number with no context. We don't really know what it means. But if the return is 12%, we can compare 12% relative to 7% cost of capital. That's a good project. Here's a table with some other numbers in it, and it has a time 0, 1, 2, and then the NPV. The cash flow is, in year one, it's a cost of $6,128. That's time 0. At the end of year one, we're going to get $2,500, and at the end of year two, we're going to get $5,000. So when we look at that, if you just add them up, the sum of all the numbers with no discounting is $1,372. So it looks like a good deal. It's profitable that way. So then we start doing some trials on these numbers. So let's think this through in terms of an example. We say that we're spending $6,128 in order to generate cash of $2,500 in year one and $5,000 in year two. If we don't do any discounting at all and just add up the numbers, we get $1,372. Now, if we discount the cash flows at 10%, we discount the $2,500 back one period at 10% and discount the $5,000 back two periods at 10%. That gives us a net present value of $277. It's still positive, right? So if we do another run and we discount, instead of at 10%, we do the discounting at 20%, we get a net present value of minus $572. So what happened between those two, between 10% and 20%? At some point, the net present value crossed from positive to negative. And if we solve it, that actually happens at 13%. So that's the point where we were discounting it enough to draw all the value out of it. So in this example, we have to keep iteratively guessing and solving for different discount rates until we converge on the answer. IRR is really tough to do, again, by hand, because you have to do each one of these calculations. But it's really easy to do in Excel, because built into Excel is an IRR function. And there are many tutorials online that'll show you how to use that function. You can just Google IRR in Excel, and there'll be a 3-minute tutorial that'll tell you how to do that. It solves the polynomial equation, finds the root, sets it to 0, and gives you the solution automatically. Very clean and neat. And that's the way I suggest you do it.